box is 1 centimeter thick and is made of copper of density that. The box in the shape of a cube of internal length 1 meter. The copper and the air inside are at thermal equilibrium. The air is at temperature of 26.85 and the copper is heated with a small 100 watt heater. After 1 minute, how much heat has been added? So that's power multiplied by time, because power is work over time. So work is power by time. The power is 100 and the time is 60, so that is 6,000 joules. So B, what is the mass of the copper and of the air in the box? So the mass of the copper, remember in density is mass over volume, so mass is density by volume, which is 8940 by, and we're told the box has the copper around it, and it's 1 centimeter thick. So roughly the volume is roughly 6 of these cuboids. Now it's not exactly this, close enough it'll be fine, it's roughly this, where it's 1 centimeter, and then this is roughly if I just draw this here. So if I cut this one here, it's going to be a little bit too big, and if I cut it here, they're not all going to be the same though. We'll just say roughly 1 meter this way, and 1 meter this way, roughly. So that's 1 by 1 by 0.01. Okay, so that is, divide this by 100 basically, 89.4 kilograms. What is the temperature of the box and the air after 1 minute? So all the energy went into heating the copper and the air. Oh sorry, not in the air yet. Mass of the air, the density by volume. The volume is 1 meter cubed, so it's just the density of air, which I haven't given you. Normally we use about 1 or 1.4. So let's actually, since I have Google open here, let's get the exact one. .225. Okay, so we'll use that. 1.225 kilograms. What is the temperature of the box in the air after 1 minute? So, that 6,000 joules went into heating the copper and the air. So, M, heat capacity of copper is 385, delta theta, plus M, and then the heat capacity of air is 1012, and then that's 1.225. Delta theta, so then delta theta will equal 6,000 over 89.4 times 385 plus 1012 times 1.225. Let's calculate. So that's 0.168 of a degree warmer. So the final temperature was initially at 300 Kelvin, so that's 300.168 Kelvin. How long until the box reaches 100 degrees? So, since everything is linear, we can actually see that the change in the temperature per change in time is 0.168 kelvins per minute. So, we want 100 kelvins. So that will take 594 minutes, which is 9.9 hours. Which is 9 hours and 54 minutes and 19 seconds. Okay. E. The tank is filled with water at a temperature of 26.85, the original temperature everything was at, and the heater is turned off. How hot will the water be in the tank? So the water is obviously going to gain energy because it's being put into a hot tank. And that's going to be equal to the energy lost by the copper and the energy lost by the air. And I think, let's see, we have our information here. So if we're putting water into a 1 meter cubed container, its mass will be 1,000 kilograms. So that's M C delta theta. So it starts off at 100 and goes down to X. That's equal to M C delta theta. So it starts at doesn't start at 100. It starts at 300 Kelvin and will increase to X. So that would be should have been X minus 300 Kelvin, or 26.85 degrees Celsius. Okay, this one is starting at 100 and drops down to X, as is the other one. M C, and from 100 down to X. Okay, let's clean up the right hand side first. 89.4 times 385 plus 1.225 times 1012. So that is 35658.7 100 minus X, and then this is 4181000 X minus 26.85. So 4181000 divided by that last answer, I got 117.25. 117.25 X minus 26.85 equals 100 minus X. So 117.25 X minus 3148.18 equals 100 minus X. So 118.25 X equals 3248.18. $27.47. Celsius. So if we just put this in Kelvin, since I gave the temperature in Kelvin, it would only seem right. 300.6 Kelvin. So gained a tiny amount of energy or temperature, but this makes sense because 1,000 kilograms of water will require a tremendous amount of energy to heat it up, much more than a bit of hot copper and air can provide.